video is about finding an exponential equation. Let's examine a question. You are a biologist working with a new bacteria in the lab, and you've noticed that it multiplies by the hour. The following data on the number of bacteria cells in a petri dish were collected at 12, 16, 20, 24, 28, 32, and 36 hours after you first started working with it. Given the data, what type of function would best fit the growth of this bacteria, and what would be your resulting equation? Alright, so we've got the number of hours here, and the first thing you might notice is that we don't have 1, 2, 3, 4 hours, but the good news is we do have equal intervals. So each of these intervals is 4 hours long. They didn't collect the data every single hour, but they're even, which means I can use the difference between the number of cells here to try and determine what type of growth we're looking for. So the first thing I might examine is whether or not I think this is a linear relationship. So to examine whether it's a linear relationship, I just want to look at the difference here. The difference between 449 and 375 is 74 cells. The difference between 538 and 449 is 89 cells. The difference here is 106, 128, 152, and 183. This does not look like a linear function. Remember, if it was a linear function, we would see a constant change, a constant value that's different here. It would be 74, 74, 74 all the way. That's not what we're seeing at all. So the next question I'm going to ask is whether or not it could be an exponential growth function. If it's an exponential growth function, then I'd be looking for some sort of constant ratio or constant percent change. A constant ratio or constant percent change. So let's look and see. To determine whether or not the ratio is the same across, what I want to do is I want to take the ratio here between these numbers. And that's going to be 449 minus 375 divided by 375, and I get 19.7% increase. When I do it here, 538 minus 449 divided by 449, I get an increase here of 19.8%. And as I go across, I'm going to see these ratios. What I can tell here is that I'm increasing each time by a very similar amount. Yes, these are not identical, but they range from 19.7% to 19.9% growth. That's pretty close. And remember, we've talked about this before with our regression equation. Our data aren't going to be exactly all the time in real life like what the model is. But the line is going to fit the data pretty well. And if this is exponential growth, we know it's going to look something like this. So, now that I see this, I think, yes, there is an exponential growth function that will apply to this data. And I know that the format for that is that g of x is equal to a times b to the t. So I need to figure out what is a and what is b. Well, one of the ways I can do this is I can use the data that I see to set up a ratio. So for example, AB at 32 hours and AB at 28 hours. AB at 32 hours is equal to 924. AB to the t at 28 hours is 772. So let's just set up a little equation. We know this is 924 and we know this is 772. So I can actually do this. AB to the 32 divided by AB to the 28 is equal to this ratio, 924 divided by 772. Well, using some simple rules of algebra, I know that I can cancel out my a's, and then I can actually turn this into b to the 4, because it's b to the 32 divided by b to the 28 is equal to b to the b to the 32 minus 28, which is equal to b to the 4. So now I have this ratio, and my b to the 4 is equal to 1.197. To get rid of this fourth power, I'm just going to raise both sides to a quarter, and that's going to cancel these out. So I get b is equal to 1.197 to the fourth power. B is equal to 1.046. Now in our function for constant growth, an exponential growth function, we know that b is called our annual growth factor here. And we know that b is equal to 1 plus some sort of rate of change. So that r is going to be 0.046, which means the rate of change is 4.6%. So, using that, here's what I can do. I can now plug in into my equation to solve for A. So A times 1.046, and let's use 28 again, is going to be equal to, remember, 772. So 772. So A is equal to 772 divided by 1.046 to the 28, which is going to be equal to 219.32, which would give me a function that looks like this. 219.32 times 1.046 to the t. Well, before we go ahead and just declare this the answer, let's plug in some data that we didn't use to calculate this equation to make sure that it works. So let's go all the way back to the very beginning at the 12-hour collection point. At t is equal to 12 hours, we see that it's 375 bacteria. So let's just plug it in. We're expecting that AB to the t is going to look like this. 219.32 times 1.046 to the 12, we're hoping will equal 375. When we actually calculate it out, we get 376.2, which in my mind is pretty darn close, and I'm willing to say that our function over here is in fact an accurate representation of the data. Because remember again, it's not going to be perfect. We're going to have data outside, but that is essentially what our equation should be. So the answer is going to be the exponential growth function that best fits this data is modeled as g to the x is equal to 219.32 times 1.046 to the t. I hope this has been a helpful video to help you understand how to find an exponential function when you know that that's what your data models. Thank you for listening.